Hello, my name is Oliver Schmidt. This session is about A2Stream, a program for glitch-free, high-quality internet audio streaming on the Apple II. The requirements for A2Stream are either an enhanced 2E, including extended 80-column card, or a 2GS. Additionally, you need an A2 Radar System Ethernet 2 card. I will give you a very quick demo for all of you who haven't seen A2Stream before. After startup, A2Stream automatically gets an IP address and prompts for the URL of the file to stream. Such an A2Stream file is specifically generated for the A2Stream program. The project website contains URLs of several sample files I have generated. As mentioned before, we'll start out with the internal speaker of the Apple II. Okay, now let's switch to the external speaker.
Ain't got time to kill, I got time to feel. I took the red pill. I know life's short, so I wanna live real, but how's it supposed to feel?
And finally, this is how it sounds when the audio output of the Apple II is directly fed into the recording device.
How's it supposed to feel?
So, here we are back on the slides. A2Stream is built around pulse width modularization. So, you may ask, why didn't I instead use pulse density modularization? In fact, I started with pulse density modularization. I had in fact a complete working implementation of an internet streaming program based on pulse density modularization. But I wasn't satisfied with the quality. And later on, I had a discussion with Michael J. Mahon on Usenet, and he explained why he considers pulse width modularization to be superior. I was convinced, so I started all over and tried again, and so here we are. Let's take a look at pulse width modularization. You want to create an output signal that you can vary, but you can only actually turn it on and off. So what you do is, over time you turn it on and off in a certain way so that the overall output power is somewhere in between. Here the output power is pretty low. You see there are only little gray areas and the lamp is pretty low lit. When you now increase the time where the signal is on, the gray areas get larger and the lamp gets brighter. And now it's low light again. So this looks very nice. Unfortunately, it's not that easy in reality. you can only switch the signal on and off at certain amount in time. For an electronic device, this is usually the clock rate. And then you have the pulse rate, which is the frequency of switching the signal on. And then you have the duty cycle, which is the percentage of the time where the signal is on, like, for example, 20% duty cycle. And then you have the resolution, which is the number of bits necessary to express the amount of distinct duty cycles. For an 8-bit resolution, that means you have 256 duty cycles. But now compare the upper and the lower row. For a given clock speed, there's a trade-off between resolution and pulse rate. In the upper row, you have a lower resolution, which means a higher noise level. And in the lower row, you have a lower pulse rate, which means you have a higher risk of noticeable carrier frequency artifacts, like when you have a lamp, that would mean you see it flicker. Okay, so what are the actual values for A2Stream? We have a target pulse rate of 22 kHz. It's the same as Michael's DAC 5-2. I wasn't anymore in experiments after having tried the pulse density modularization. So, what is our clock rate? You might think of being it individual instructions of the CPU. But this isn't true. A2Stream uses individual machine cycles as clock rate. This is although the instructions we have all require several machine cycles. Okay, so what is the possible resolution for the target pulse rate given? With 1 MHz, this means that we have 46 machine cycles per pulse. But that doesn't mean at all that we have easily 46 distinct duty cycles. Let's have a closer look how we generate duty cycles using the 6502 CPU. Here you see the shortest duty cycle possible. It starts with toggling the speaker with a store accumulator instruction, and then right afterward another instruction of the same type. Then it spends some cycles doing something, and then it jumps somewhere. If we add this up, we see we have 4 plus 4 plus 35 plus 3 equals 46 cycles. Now let's have a look at the longest duty cycle. Again, we start with toggling the speaker, basically say turning the speaker on if you want. Then we spend some cycles, and then we do the second speaker toggle, meaning to turn it off if you want to put it that way. And then right afterwards we jump somewhere. You see, again, 46 duty cycles. But if you look closely, you can see that these are the two edge cases. The first few duty cycles you could imagine are just not possible with that CPU. The same goes for the last few duty cycles, because you have these additional operations and the additional jump. So A2Stream implements, after all, 36 distinct duty cycles in these 46 machine cycles. By the way, DAC 5-2 implements only 32 distinct duty cycles in the same 46 machine cycles. Using machine cycles as clock rate requires that for the 36 distinct duty cycles, there are 36 distinct pieces of code. Every execution of one of those pieces generates exactly one pulse. Running the same pulse generator several times keeps the speaker in a certain position somewhere between low and high, just like a pulse width modulated controlled light bulb keeps its brightness. Running different pulse generators in a sequence moves the speaker, just like a pulse width modulated controlled light bulb would fade in or fade out. The task of A2Stream is so to run those 36 pulse generators in a sequence that reflects the changes in the audio signal. Every pulse generator ends with a jump instruction. This instruction plays an important role in the overall architecture of A2Stream. So let's have a closer look. The 6502 is an 8-bit machine, but its address space is 60-bit. The address space can be seen as 256 pages of 256 bytes each. Each address consists therefore of 2 bytes. The so-called high byte denotes the page, and the so-called low byte denotes the offset into that page. Therefore, a jump instruction consists of 3 bytes. First, there's the opcode, then there's the target offset, and then there's the target page. A2Stream modifies every target before executing it. A2Stream can spend the cycles to modify both bytes of a jump target. So we have 2 options. The first would be to only modify the offset, meaning that all pulse generators would have to live on the same page, but that doesn't fit. The other option is to only modify the page, meaning that all pulse generators are on the same offset on each of the pages. That's what we do. So the 36 pulse generators are on the 36 pages of hex 40 to hex 63. This is just behind the high-resolution graphics screen. So all a pulse generator has to do with the cycles so far just spent would be to first get somehow a byte with a value between hex 40 and hex 63, and then set the jump target high byte to that value. If we had a hypothetical data source that delivers a new value on every access, we would be pretty much done. But in reality, we are interested in streaming data over the internet. So we need to have a closer look at the network aspects. A2Stream uses the A2Ratio Systems Ethernet 2 card, which is built around the WithNet W5100 Ethernet controller. That controller contains a TCP/IP stack, but most Able2 programs rather use their own TCP/IP stack. So why is this TCP/IP stack aspect important to us? Usually, a web client wants to receive the data much faster than a web server can send it. It's just waiting. In contrast, A2Stream needs to receive the data much slower than a web server usually wants to send it, so the web server needs to be throttled. And A2Stream fully relies on the W5100 TCP/IP stack to autonomously take care of TCP flow control, which provides that very throttling. So from the network perspective, the W5100 chip is just great. But from the perspective of accessing it, being the host, it's not that easy. Receiving TCP data with a chip means to first check if it has data available, then compute the address of the data in the W5100 RAM. Then you can read the individual data bytes from the chip. And finally, you have to commit the number of bytes you have actually read. The steps 1, 2, and 4 all require way more cycles than the ones left in a single pulse generator. That means there are pulse generators that are running with no data being available. Solving this problem is the innovation of A2Stream. The first part of solving the problem is to distribute these individual steps over different pulse generators. So we end up with a 2-dimensional array of pulse generators. The first dimension is made up of the 36 distinct duty cycles. And the second dimension is made up of different pulse generator types. But does that mean that we need another set of 36 pages for every pulse generator type? We would pretty easily run out of RAM quickly. Fortunately, pulse generators are short enough to share pages. What does that mean? The unmodified jump target low byte can control the sequence of the pulse generator types, and this way the sequence of the necessary steps to take. I have visualized this for you. Here you see a lot of pages. Each page contains several pulse generator types. And each page is responsible for a certain duty cycle, starting with page hex 40. Now let's presume we are currently executing the pulse generator type 1 for the duty cycle 0 on page hex 40. We know for sure that the next pulse generator executed will be of type 2 because that's set in our jump target offset, which is not modified. However, the jump target page will be modified, so it could be possible that we execute any of those denoted pulse generator type 2 variants based on the wanted duty cycle. Now we get a data byte and actually see that we modify the jump target to point to a certain duty cycle, meaning a certain page. At the end, after the modification of the jump target, we jump there and execute this pulse generator. And then the whole thing starts all over. Now for the second part of the solution. As we've seen, the W5100 can't provide a continuous byte stream to us. So we need a ring buffer in the Apple II memory. Every pulse generator reads exactly 1 byte from the buffer because every pulse generator needs to modify the jump target high byte before it jumps. But some pulse generator types can't write a byte into the buffer because of the setup and commitment logic needed by the W5100. As a result, at least one pulse generator type must write more than 1 byte into the buffer. Efficient management of that ring buffer is a central aspect of A2Stream. Imagine you have pulse generator types that have to read 1 byte from the ring buffer and write 2 bytes to the ring buffer, all during a single pulse. If you take a look in general at a ring buffer, then there is a write pointer, a write value, read pointer, and read value. So you have 4 things to take care of. However, the 6502 has only 3 general registers, A, X, and Y. So what to do? I've chosen to abuse the stack pointer as 4th register. In order to make efficient use of this idea, you have to use 65C02 specific instructions. Let's take a look into the details. You can either choose to use the stack pointer as the read pointer into the ring buffer. Then you write in the ordinary way and read via the PLX instruction, which is PAL-X from stack. Or you use the stack pointer as write pointer of the ring buffer using the push-X to stack instruction and read in the ordinary way. The write approach is a little bit faster. Nevertheless, A2Stream uses the left approach because it needs to read from the ring buffer all the time. So this is more important to A2Stream. Even with our stack pointer trick, a single pulse generator still can write 2 bytes into the ring buffer. However, 2 pulse generators together, of course of different types, manage to write 3 bytes. So we end up with an average ring buffer write speed of 1.5 bytes per pulse. which is just enough. You see that we have quite some different pulse generators. We have these different types, and for each type we have 36 distinct duty cycle variants. Of course, all these pulse generators aren't coded manually. You need a pulse generator. You could run this generator beforehand and store the result in an Apple II binary file. However, A2Stream creates the code for all those pulse generators rather at runtime. This has several benefits, including the ability to select the Usernet slot and the ability to select speaker versus tape output. To do all that, A2Stream contains what you could call a custom assembler, which is written in C using CC65. There's only one source for all the duty cycles, because the instruction scheduling is automatic within this assembler. And you only need to write down the source that differs between the different pulse generator types, because everything else is implicit. Let's have a look at actual source code. Here's the source of two pulse generator types used for the visualization. The 6502 instructions may seem a little bit strange, but that's not so hard. The first instruction here just means load indirectly from 0 page pointer with an epsilon index. And this here is just a store accumulator on an absolute address with epsilon index. And this here is nothing to care about because it just stops the assembler. The statement never makes it into the generated code. Those two types are executed by turns, so the source code actually makes sense. It loads the accumulator from a 0 page pointer and then stores the value in the 6 bottom lines of the high-res page. And finally, it increments the epsilon register and starts all over. Please note that the code can presume both A and epsilon to be retained between the execution of pulse generators. Now let's look at the generated code. I've used colors to make it easier to follow. On the right-hand side, we have the cycles for each instruction. The sum is always 46. Top, we have the green stuff, which is for the speaker toggle. Then we have blue stuff. It's here the PLX to pull the X register from the stack, and then a store X to modify the jump instruction down below. The orange stuff is specific for this pulse generator type. It's sort of the business code of this pulse generator type. Here it's the left part of the visualization that we saw before. And finally, we have the gray part. Here we are spending some cycles without actually doing something. We're using two types of instructions here. The no operation always takes 2 cycles. So if we have an odd number of cycles to spend, we additionally use a branch instruction which spends 3 cycles. As you can already see by now, having to spend exactly 1 cycle is an issue. We'll see about that later. Here we now have the duty cycle 0 on the left-hand side as we saw it before, and additionally the duty cycle 1 on the right-hand side. Duty cycle 1 needs to have an additional cycle between the 2 speaker toggles. Here it's 4 and there it's 5. As mentioned before, there is no 6502 instruction taking exactly 1 machine cycle that we could put in between those 2 accesses to the speaker. Therefore, we take the approach of using a different instruction to access the speaker for the second time. Here it's an instruction taking 5 cycles. It's a 65CO2 specific instruction accessing the speaker via the 0 page, but not requiring any additional register for indexing. And you see here, we have 3 instructions left, and there are 2 instructions left. So overall, the sum of instructions stays the same. Don't be afraid. I don't want to go through all the duty cycles in that detail. However, there are some more points to look at. Here, we for the first time have room to insert an instruction between the 2 speaker toggles. Here, it's a branch instruction. The other point to look at is, here we spend 3 cycles, so still there's no room to put anything here below inside that gap. With duty cycle 4, we can for the first time put an instruction that we actually need between the 2 speaker toggles. From now on, just look how this green line here moves downward for the following duty cycles. The last 2 duty cycles are interesting again. 35 starts with its first speaker toggle, then executes quite some code, does its second speaker toggle, and then goes right into the jump statement. But 34 is again interesting. As seen before, we cannot have another statement inserted between the speaker toggle here and the jump statement, as there's no statement with just 1 machine cycle. What we do instead is doing the jump before the second speaker toggle. The second speaker toggle isn't actually part of duty cycle 34. Rather, the second speaker toggle is prepended on each and every duty cycle that exists. So duty cycle 34 jumps at this special code, then has here its second speaker toggle, has the desired 4 cycles spent, and then falls into the normal execution of the next pulse generator. Now you've seen the actual code of the pulse generators, and you've seen how A2Stream manages the fact that there's no instruction taking only a single machine cycle. But it doesn't end here. I've said before that several pulse generator types can share a page. In fact, up to 5 pulse generator types can share a page. But A2Stream has 10 pulse generator types. So a second set of pages is necessary. It's on the 36 pages hex 64 to hex 87. Every pulse generator type is either in page set 0 or in page set 1. The data needs to contain either hex 40 to hex 63 or hex 64 to hex 87, depending on the page set the next pulse generator is in. So the data needs to exactly match the internal A2Stream structure. Is this considered to be a bug? No, it's a feature. Let's have a look at the actual program flow through the pulse generator types. We start with initializing the data block transfer at the W5100. This takes several pulse generator types as explained before. In fact, there are 3. After this, we can finally start to actually transfer data into our ring buffer. As mentioned before, they require 2 different types in order to transfer 3 bytes. We have here a loop transferring 3 bytes after 3 bytes after 3 bytes. But at some point, we need to stop doing that, of course. When we have stopped doing so, we commit the data. Again, we need several parts. Here, there are 2 parts. Okay, and at this point, we usually would have a loop variable check to see when we want to quit the loop. But A2Stream has no cycles to spend for such a check and for such a branch. So we put these pulse generator types into page set 0 and these pulse generator types into page set 1. And we make sure that those two pulse generator types have the same offset. Then the data can quit the loop by just switching between the one value range into the other value range. So while having values of page set 0, the loop continues, and then having a value of page set 1, the loop is quit. So the program flow here is determined by the data received. Finally, you see all 10 pulse generator types that make up the core of A2Stream. 5 of them in page set 0 and 5 of them in page set 1. Inside each page set, the data flow is determined by the jump target low byte, which is not modified. In both cases, that data flow ends in an endless loop. The data breaks the code out of the two endless loops by setting the jump target high byte to a value pointing into the other page set. The transition from page set 0 to page set 1 corresponds to the ring buffer being full. The transition from page set 1 to page set 0 corresponds to the buffer being almost empty. So the overall data flow inside A2Stream is a choreography of parts being managed locally and parts being data-driven, and they work together without having any local state. Several times I touched the topic visualization, but didn't really cover it. So let me do now. The visualization is completely pre-computed by the A2Stream file generator. It consists of 140 visualization templates that are downloaded by A2Stream before the actual playback. Each template can be either of two types: the odd bytes of a double high-res line to be placed in main memory, or the even bytes of a double high-res line to be placed in aux memory. Every 256 data byte is a visualization value that is inserted into the stream of audio data. There's one pulse generator type that therefore reads 2 bytes from the ring buffer, the usual audio byte and the additional visualization byte. That visualization byte selects one of the 140 templates. Then the selected template is copied into the bottom 6 high-res lines by the 2 pulse generators. So now let's have a look at the actual memory layout. Similar to the duty cycles, every template is on a different page at the same offset. The 140 templates are on the pages hex 10 to hex 1b and pages hex 40 to hex bd. The pages 40 to 87 are shared with the pulse generators. There's a little bit left on each page that can be used by a template. The A2Stream player runs completely in aux memory, and there's no main to aux memory copy. Rather, the double high-res data for the cover art and the templates are loaded from the W5100 directly into aux memory. And the pulse generators are generated by the C program running in main directly into aux memory. This works by the highly optimized C code placing all relevant variables in the 0 page. So we don't use Alt-CP and therefore have no issues with the duplication of variables. The trampoline in the language card sits above the ProtoScript code. It acts as a chunk between the code in the main memory and the code in the aux memory. Let me visualize the overall memory layout. Here you see the main and the aux memory. The light gray areas are free and the dark areas are reserved. First, we load the binary into main memory. Right after loading the binary, we move some of the code as trampoline into the language card. Then the program starts to run, uses its BSS and its stack. Additionally, it uses the heap. Then the program generates the pulse generators in aux memory. Then the double high-res graphic is loaded from the wire. And finally, the visualization templates are loaded. So you see here how the memory looks like during the actual playback. That's all. Thanks. And now for the Q&A. I will ask a question myself and will answer it. The question is talking about streaming audio via the internet. The question, I think, would be, can you do live streaming of audio over the internet? And the video that you have just seen is a little bit shorter than you would have expected. That's because I hoped that I would be able to show you something. And I actually finalized it this very day. So it's really brand new, and you are the very first persons to see it. Let me try to show this to you. Okay. So here we go. I have created a program that works as a minimalistic web server. It's not actually a web server. It's just enough of a web server to make A2Stream believe that it is a web server. So the unmodified A2Stream program is willing to connect to it. The program itself is more like a proxy server and a converter that takes an audio live stream and converts it for A2Stream. I've tried several different ways to do this in an efficient way without, let's say, inventing the wheel once more. And I found a way that works out pretty nicely. That is using the M player and feeding the M player output that would normally go into a sound card instead into my program. So let's see how that works. I start with starting this new program. It's serve A2Stream to the bottom left. And you see it starts and waits on a named pipe for the audio data. Then I have here a shell where I start the M player. You see there are quite some special parameters which are really handy here. For example, I can normalize the volume, which is great because we don't have that much resolution. So we have quite some noise. So the audio should be quite loud all the time. Here I'm doing a resampling. You see it's not quite exactly the 22050, but it's a little bit higher, which is just what I need. And the rest here is whatever. And from here on, you see the actual URL that I'm streaming. It's the HTTP internet radio stream, standard a radio stream, MP3 from a local radio station that I like to listen to. Okay, I will start this here. And you can see it's now start playing, and it's saying, okay, I'm connected on the pipe. So the two programs are connected, and the audio is in fact already streaming from the M player to my serve A2Stream program. Now I can bring up A2Stream. For the sake of simplicity, I'm doing this here in the emulator. And I will just enter the local URL And it should.
I wanna hear you call my name. I wanna feel your touch on me again. When you're gone, I can't go on.
So that was just what happened to be playing right now at this radio station. If I end the playback, you see on the bottom left, it says disconnect from A2Stream. I can easily just go here to the emulator, bring it up again, and I would see another connection. And we'll bring up the live audio again. Okay, so this is what I wanted to show you. Okay. This is right now just a local program running on Windows, but you could easily transfer it to a Linux program. You could pretty easily create a program from it that can have several clients or several audio streams. And you could, if you wanted to, create some public service from it where you allow other persons to stream really over the internet, given the URL of your server. Okay, that's what I wanted to show you. Now I'm really open for questions.
There's a comment from Rockers. Someone wants to thank you for providing the source code on GitHub.
Okay, yeah, you're welcome. I hope you enjoyed it. Actually, I have always wanted at one day to give a presentation, Kansas Fest, but it was clear to me that the travel from Germany would be too costly for me. And so the fact that we now have a virtual format is the one that allows me to fulfill my dream of giving a presentation here.
Thank you, Oliver. That was super impressive.
Yeah, thank you for the nice feedback. I will, of course, be present in the Discord channel over the next time. So is there something coming up on your mind? Just ask there. Okay, bye then.